So first I can save you the story, I think, because we all know the story very well in this room. Yeah? So I will concentrate on, can the cracks grow? Yeah? What are the hydrogen risks? How can they be explained? Do they grow? Yeah? And we will have a look at new inspection data. And I will try to combine this with some new research results to come to some conclusion. Yeah? So the story, I can skip this, it started all in 2012, maybe the dates are important, with the inspection of the nuclear power plant Doel 3, yeah, where a new instrumentation was used to check for underclad cracking. Underclad cracking was not found, it was a problem that was observed in some French reactors, but it was not found here. But thousands of defects were detected in the pressure vessel wall. Yeah. The same was then done in Tihange 2, and there are some people from Electrabel, and correct me if I say something wrong, yeah? But similar things were found, although it was said to somewhat lesser extent. Also in the Belgian media, it was a big issue, and so on and so on. And I added this map to show the location of the two reactors from my German friends, my American friends. I also included the map of Europe to indicate where Belgium is. Yeah? So this is how it looks like, different rings, as you will know, different rings of the reactor pressure vessel, welded together, and so with a total height of approximately 30 meters, diameter 4 or 4.4 meters, with a wall thickness of 20 centimeters, low alloy steel, essentially carbon steel, you could say, and with, at the water side, at the primary water side, a stainless steel lining made from an alloy, something like AISI 308 or 309. Yeah? So what were the major findings? Yeah? So the findings were unexpected, as I said, and there were various questions with the new technique, the new instrumentation, is it correct what we measure, and so on. And so there was a big issue. But as you heard already, there were up to 40 indications, defects that were detected in some sections of 1 cubic decimeter. Initially, in 2012, a number came up like 7,700, and so later on that was corrected for Doel to more than 13,000. And they were found to a depth inside the wall of 30 to a maximum of 120 millimeters at the water side. Yeah? Now, this could be explained due to the thermomechanical history of the model, and that was, and some modeling was done by SEK, the Belgian Center for Nuclear Research, and they said it can be associated with some what is called ghost lines and so in the steel and so on. So there was some metallurgical explanation why these were concentrated in these areas. A number of investigations were carried out, and as was discussed already during the press conference, the root cause that was identified were hydrogen flakes or hydrogen flaws. Yeah? In Dutch it's called vlokken, also in German flocken. Yeah? Now this is really a euphemism. If you look at it from a metallurgical point of view, then you will see that at the top you see a cross-section of a stainless steel sample, and this is the fracture surface. If you look at this, this is a brittle fracture at a small scale, but this is simply a brittle fracture. And it's really a euphemism to talk about flaws or vlokken or whatever. The reason was explained is the difference in solubility of hydrogen in the steel melt and a lower hydrogen solubility at room temperature. And this excess of hydrogen, it will, from a metallurgical point of view, it will concentrate mainly at inclusions, like sulfide inclusions, or oxides, and that's why the chemical composition of the steel is important. Yeah? So, but these are spherical cracks typically. Yeah? It's a known phenomenon from the 1960s, yeah? These hydrogen flakes, but they are almost spherical, but in fact they are hydrogen-induced brittle fractures. Yeah? Now, fortunately, it was detected that most of these were laminar or quasi-laminar along the vessel wall, which is fortunate, of course, but there were some high densities, and I will show you what it means being laminar or quasi-laminar along the wall later on with some practical examples. So, can they grow? Yeah? These hydrogen flaws. Originally, it was said in the investigation process that currently there is no new source of hydrogen anymore. So it was assumed that they would not grow, that it was a manufacturing defect, and they were sitting there. But then I started thinking, well, there is something like a cathodic corrosion reaction. We'll come back to that in a minute. And in the water, of course, primary water, we have some radiolysis, yeah? And they also produce other effects. Also, typical sizes of hydrogen flakes from the manufacturing, they have a typical size of 4 to 15 millimeter, say a fingernail, approximately. Yeah? Now, what was found already in the original inspections were flakes or cracks, defects that were larger, 20, 25, 30 millimeter and so, which was a bit suspicious. And there was a question, indeed, in the water chemistry, as we run the system, what will be the cathodic corrosion reaction? Let's come back to that, yeah? So, if you have corrosion, so attack of a steel, you have this reaction. You generate iron ions, and you generate 2 electrons. Now, we have to get rid of these electrons in the reaction, and that's balanced by a cathodic reaction. And the cathodic reaction is the splitting of water with the production of hydrogen atoms at first. And 2 of such hydrogen atoms, they combine into an H2, a hydrogen molecule, which is a gas. And that's illustrated, if I can run this again. But maybe you've noticed this, when you put the steel in a beaker with the corrosive fluid, there were some gas bubbles coming up. That's typically the hydrogen which you generate, yeah? And this is important in the whole story. Because if you generate new hydrogen atoms at first, this is an electron microscopic picture with all iron atoms, yeah? And the hydrogen, which is very small, it will simply move through the iron lattice, and it will collect at some folds in the material, yeah? And so, coming from an RPV, 20 centimeter thick steel, yeah? It's in fact at the atomic scale that you have to look, and that it's important, yeah? So and then we started making, what can be the cause of that, yeah? Or what can be the result? Well, the hydrogen atoms, they can simply move through the metal lattice without any problem because they are so small. But when they enter into a void, like the hydrogen flake, 2 of these atoms can combine to a hydrogen molecule, H2, and that's simply too large to escape from it. And that will build up internal pressure. And this is illustrated in these pictures, and I will show you something later how it works in practice. Now, how many hydrogen is produced, for instance, in a corrosion reaction? Yeah? And that's quite a bit, as we will see later on. So, because I said, well, it's not correct to say that there's no new source of hydrogen anymore, I produced together with a colleague of mine, Mr. D.B. McDonald from the University of Berkeley, well-known expert in the field, and nominated France for the Nobel Prize Chemistry even and so. And we produced a paper for a conference in the US, Corrosion 2015, which also ended up into the media even, where we demonstrated that what the process generated hydrogen during the operation was not so innocent. Yeah? And this is shown over here. Just for the cathodic corrosion reaction, if you assume of the stainless steel a corrosion rate between 0.1 and 1 micrometer per year, which is realistic, yeah, in that kind of water, you produce something like 28 or 60 moles of hydrogen molecules per year, yeah? Which is 2 times 10 to the 24 to 10 to the power 25 atoms per year of hydrogen atoms, yeah? That you produce in 1 year of operation. And this you pump through the metal wall, yeah? And that's a lot, eh? That's a million times a billion times a billion of hydrogen. And we came up with a total volume of 1.3 cubic meters that you possibly pump through the wall. Now the question is, how much of the hydrogen enters the wall and how much escapes as hydrogen gas in the water, yeah? And there are many uncertainties and it will depend on radiation and so, but some sources, they say that even up to 90% could be absorbed into the steel metal, which is a lot. Let's even assume when it's only 10% instead of 90, it's still a lot. And that's just for the corrosion hydrogen. Yeah? Radiolytic hydrogen, so produced by radiolysis of the water, is not even unaccounted for. And that has later been modeled by my colleague MacDonald. Yeah? What is the real risk? The risk is that some of these cracks, yeah, they can link together. And this shows a typical hydrogen-induced crack taken from some standard works and so. And it's a recognized problem by API, the American Petroleum Institute. It's a very well-known process there. And API has produced special standards for the purity of the steel just to overcome this. And I have brought one example here of, it's not from a nuclear system, yeah? It's from a petrochemical system, but this is also quite a few centimeters thick, yeah? And indeed, it starts with very fine cracks, yeah? As you can see here, yeah? Very fine. I'll pass it around to the room. But due to the process-generated hydrogen, this is what happens, yeah? So interlinking, and when Electrabel says they're only thin like cigarette paper, it's great in the beginning. Some of these are like that, but this is what can happen. Just to the high hydrogen pressure building up in such a void, yeah? And so it bulges, yeah? So that's called the hydrogen blister, yeah? But you should also see that the cracks can interconnect in between this, yeah? And this is the real danger. If you want to take it. So this is what is recognized in the chemical industry. So going back to the situation and having a look at it again in 2015, reporting that there is currently no source of hydrogen anymore, it's a mistake, yeah? There is hydrogen from the cathodic corrosion reaction, from the radiolysis. Coming then back to the new inspections, inspection data from 2014 that were released mostly in 2015, then we saw that the typical sizes for hydrogen flake, as we said, is 4 to 50 millimeters. Now we had 13,000 cracks in blue, more than 3,000 beyond, with maximum sizes of 18 centimeters by 7 in blue and 15 by 7 in beyond. That's not a fingernail, that's like a hand, yeah? And that's also what you see in the sample over there. So then there was a lot of discussion, also within Funk and with other experts, and the discussion was basically this hydrogen that enters into such a flaw, yeah, can it escape again or not? Yeah? If you look at textbook knowledge from chemical engineering, it is assumed that it cannot escape. The hydrogen molecule is too large. But there are some physicists that have been calculating diffusion laws and so, and they say it can escape again. Yeah? But this is against all what we know from chemical engineering practice. And also, if you look at the parameters that have been used, there's an uncertainty of 5 orders of magnitude on the diffusion coefficients at low temperature. Yeah? And the best proof that hydrogen gas cannot escape through a steel wall is simply when you have a gas bottle with hydrogen gas. The hydrogen will still be there after a couple of years. Yeah? It will not escape from it. Yeah? So, and this was a whole discussion. So the basic question is then what happens, especially during an outage or an emergency shutdown, yeah? Where we could have a pressurized thermal shock. Yeah? That's even worse. And even people from SEK, the Center for Nuclear Research, that made some calculations, said hydrogen can escape from the thing. They came up in their own report, which I have with me, that during emergency shutdown there is a risk situation, a high risk situation present. Yeah? So, coming to the end almost, also Funk has a technical auxiliary called BEL-V, and even in a report from November 2015, they stated themselves that the situation was not as it should be. And they said that in 2014, the data compared to 2012 have substantially increased, much more than expected. The size was larger than in 2012. And more importantly, because there was the issue of the sensitivity of the measurement and so, more importantly, what the conclusion was that such large flakes as we have, that they were practically excluded from metallurgical considerations. It's from their own report, yeah, page 15. They also say, most important, on page 17, that the results do not allow to claim that there is an experimental evidence of no in-service growth. It's a difficult sentence, but that's what's said in the report from Bellevue. Nevertheless, Funk authorized the restart of the reactors based on a report from International Review Board, but there was a minority opinion in the report, yeah, which is not often talked about, but there was a minority opinion. Fortunately, also Funk ordered that there needed to be a new inspection after 1 year of operation of the reactor. Yeah? So and this was a public version, again, at that moment. The director from Funk, he said, these are no cracks, het zijn geen scheurtjes. Yeah? There were flakes again. Yeah? It was also said that they would never reach the wall. And also it was claimed that there was no previous experience. Now, if you look at the 25-year-old journal, Journal of Nuclear Engineering and Design, there already was a discussion on hydrogen corrosion of pressure vessel steels, nuclear pressure vessel steels. And this is a picture from it, yeah? And if you enlarge this, this is how it looks like, yeah? They run parallel to the wall, but nothing is perfect. You see this? Yeah? How they can intersect, yeah? And how they run in theory parallel, but not fully parallel. Yeah? So the real risk now is really hydrogen-induced stepwise cracking, where these cracks would interconnect. Moreover, the hydrogen tends to concentrate at the crack tips, and there is a lot of hydrogen. Yeah? So they tend to concentrate there and will embrittle the crack tip and have further consequences. In Germany, you say it's a Brockel reactor. Yeah? You wouldn't say it's a Brockel reactor, but there are certainly Brockel zones in the material, to my estimation. Yeah? So nevertheless, the regulator, being Funk, they approved the restart with a lot of protest. Yeah? Now, coming back to some update and new inspection data, remember, after 1 year, yeah? And then the big question is, do they grow? Can they grow? The answer is yes. Do they grow? Then new inspection results from 2016 and 2017. You've seen this figure already and the doubts whether there was something going on between 2012 and 2014, yeah? I will not come to this, and I will go to new data. Of course, ultrasonic inspection is not very easy. Yeah? This is a typical image. Yeah? And how many cracks do you see here? Yeah? And are they interlinked and so on? So just a warning about that. Now, Funk, or AFCN in French, they came on their website with a message. In 2016, no evolution of hydrogen flakes in Doel. Hallelujah. And in May 2017, a year ago, the same no evolution of hydrogen flakes in Tihange 2. Identical message. Yeah? Now, under pressure of some people in the room, for instance, yeah, some results, some data, some reports had to come on the table. And this is what we read in the reports. The first one is, how do you measure the evolution between 2014 and 2016? Yeah? Now, it appears that it was assumed a criterion for non-evolution. And that was not little. 6 decibel, yeah, for the ultrasonic signal. That is significant, yeah? So if the signal difference was less, no evolution. Yeah? Also something you could read. Un nombre très faible d'autres indications non notées en 2014. So a small number of indications, ultrasonic indications, not seen in 2014. Yeah? And also further on, quelques rare indications, few rare indications that pass that criterion for non-evolution. Yeah? So that's already a little bit different message. Yeah? And there are some more of these, and I will not go into detail for this, yeah? But nevertheless, in the reports, you could read concerns about impact of this on structural integrity, about the noted evolution. Now, what I understood was from the public message that there was no evolution and that there was no impact on structural integrity. Nevertheless, this was obviously a concern. Now, finally, the extensive inspection reports had to come on the table. And I took the time during my summer holiday period to have a look at all the appendices of the data. Yeah? And I will concentrate on those with the hunch too. The real data, what did they show? So-called 60 new indications were found in 2017. In contrast to the public message from Frank, no evolution. But fortunately, hallelujah again, if people looked again at the original data from 2014, also these 60 defects, they were present. And then it becomes interesting because if you then look at how do these 60 new compare to the situation in 2014, because you can at least statistically identify them, then this is the comparison. This is how many. Yeah? And this is whether they decreased in size, yeah, or increased in size. The biggest peak you see there, the difference in measurement was between half a millimeter minus and half a millimeter plus. Yeah? And of the 60 new, 9 were smaller, yeah? But in view of the measuring differences, of the measuring difficulties, of course, physically they cannot become smaller. Majority, same size, but 31 showed an increase, 31 of the 30. Yeah? And if this would be statistically insignificant, then you would have a Gaussian distribution, which you definitely don't have. Yeah? So also for Doel, I have done some investigation. There are some identified cracks that if you not detected in 2012, having grown in 2014, this is on a comparative scale the situation in 2016. These are data from Arriva, the inspection agency itself, and from Frank. Yeah? So, but the official message was no new cracks and no growth of these cracks. All this puts a little bit together that possible evolution, yeah, with results from my other colleagues from Leuven, which were presented earlier and which you will hear tomorrow. Yeah? But also internationally, there were more doubts and so on, and my colleagues produced a nice report about critical reflections about the integrity of the RPVs. I will not discuss that. There were also some other results, but I will skip this. It's not really important. There's one more study I want to mention. We have an inter-university educational program on nuclear engineering in Belgium. It's a national program, all universities together. You see them here. And so it's a master after master. And there was a thesis carried out in cooperation with my colleague McDonald from Berkeley University. And the conclusion from that thesis was fairly clear. I looked at the corrosion-generated hydrogen. Here merely was looked at the radiolysis hydrogen. And in different scenarios, yeah, they came up with this kind of pressures and so that can possibly build up in a void. And this is the crack growth parameter. Yeah? So they are definitely in each other's neighborhood, not to say that possible hydrogen pressures are larger than the required pressure, what you see here. Yeah? So the clear conclusion, and there has been criticism, and this is a theoretical modeling with all the uncertainties that you have and so on, but it's certainly in each other's neighborhood. So clear conclusion was that one is not able to assure stability of the hydrogen flakes in the RPV. And this is summary of all this. Ultrasonic inspections during acceptance testing, end of the 70s, twice tested at least a go. No problem with these, yeah? Inspection in 2012 versus 2014, you've seen the differences due to higher sensitivity, maybe, but you've also seen what went on with the new inspections after 1 year of operation. Moreover, the sizes, yeah, of these are not in line with what is typically a hydrogen flake, yeah? And the question is whether with such results in the vessel, whether that would ever pass acceptance testing. The answer is clear, I guess, yeah? And meanwhile, we have all the industrial experience from the chemical process industry from American Petroleum Institute, and definitely there are some possible mechanisms for the instability of the flakes, yeah? And it's really, to my opinion, running the operator, but people from Electrabil will not agree on that, but I think to my impression, it's like gambling, yeah? Whether it's really safe to keep the reactor going on, in fact, yeah? And it's simply, it's in general a problem of process equipment aging. It's not unique for the nuclear sector. That doesn't mean that I'm anti-nuclear, but once an installation is finished, it's finished, yeah? And then you have to consider replacement of it, maybe. So, this is it. If you have more questions, there is on the internet, you can find it, a report on all the problems of hydrogen in steel, yeah? And so on. Or you send me an email and I can send you a copy. Okay, thank you.